Hi everyone, I'm Rachee. I'm a PhD student at UMass Amherst. And today I'm going to be talking about the nature and dynamics of Tor exit blocking. This work was done in collaboration with folks at UMass, Stony Brook, Berkeley, and ICSE. So we know that the Tor network provides a way for users to communicate with destinations anonymously. And this is specifically important for folks like journalists, activists, and other users who are, say, behind a state-level censor, and they want to access content that's blocked for them. But recently, we've seen tensions emerge between Tor and content providers, and this is because when content providers receive traffic from Tor, they're not sure if this traffic is coming from a malicious user versus a benign user. And this has resulted in content providers differentiating against Tor users. This differential treatment comes in different shapes and forms. Sometimes content providers force Tor users into solving a series of CAPTCHAs, and sometimes it can be as extreme as outright denying access to Tor users. And this is an important problem. It's an important problem for two reasons. The first is that this lowers the utility of Tor for its users. And the second problem is it's also harmful for revenue-generating websites that are being hosted by these content providers. The reason it's harmful is because a recent study from Akamai showed that Tor users are just as likely to make purchases as non-Tor users. So this is the backdrop in which we place the work that I'm going to be talking about today. And the kind of questions that we want to answer in this work is we want to understand what are the different moving parts in this equation that leads to differential treatment against Tor users. To make this clearer, I'm going to try and walk us through an example which familiarizes us with different entities that are relevant in this scenario. So here I've got two users, user 1 and user 2. User 1 is a benign Tor user, and user 2 is malicious. Both of these users want to access content that's being hosted on server 1, 2, and 3, and they want to do this anonymously. To do so, they access the hourly published Tor consensus, which has information about the IP addresses, exit policies of Tor nodes. In the middle, I've got the Tor network. It's a simplified representation where there is an entry relay, a middle relay, and an exit relay, which has such and such IP address. On the right side, I've got three servers that are hosting popular content. But as we know that servers on the internet receive a bunch of malicious traffic. And as a line of defense against this traffic, they often subscribe to or have some form of homegrown threat intelligence, which informs them about the host names and IP addresses that could potentially harm them. So this is the setting. Now user 2 tries to attack server 1. His traffic makes it to server 1. Server 1 realizes that this is an attack. As a result, in response to this attack, server 1 lets threat intel know that this IP address is bad. An important point to notice here, server 1 does not know that this is user 2's traffic. It only sees the IP address of the exit relay. Now, supposing user 2 was trying to attack server 3, server 3 realizes this is an attack, and another possible response to this attack could be that server 3 sends an abuse complaint to the operator that's responsible for this Tor exit relay. So the way abuse complaints work is that they are sort of a notification to the person who's in charge of an IP address saying, hey, I'm receiving abuse from your network, please stop doing that. This is basically an enumeration of how could these servers react when they are under attack. Now, user 1, who's just trying to get their daily dose of cat videos, accesses server 2. But then server 2 is subscribing to the same threat intel information. And as a result, server 2 could block this benign Tor user. And this is one way in which benign Tor users could face differential treatment. Another way is if threat intel was simply crawling the Tor consensus, they would also think benign Tor users could cause trouble. So I'm trying to enumerate and walk through possible ways in which this could happen. But we want to answer questions about how often does this happen and which of these scenarios really works out in the wild. And to to do so, we introduce vantage points in this complex interaction I've got here. But we introduce these vantage points in such a way that we don't compromise the user's anonymity in any way. So first, if I could be a benign Tor user, I could quantify the impact of this differential treatment on Tor users. I could do a more fine-grained analysis of what happens when a benign Tor user interacts with popular content on the internet. If I could run exit relays of my own, I could follow through the life cycle of an exit. I could see how does this exit gather a bad reputation? What kind of abusive traffic does it see? What kind of complaints does it see? Additionally, if I could get access to these abuse complaints, then I could use these as a proxy to understand what attacks come from Tor. So I'm not really doing any logging on the exit relay. I'm just using these complaints that servers receive, and I use these to understand attacks that have been coming from Tor over a duration of time. And finally, if I could get access to threat intel, which is commercially deployed in some sense, I could understand what is the reputation of exit IPs in general? How does it change over time? So these are key questions that we try to answer in this study. And I'm going to go over each of these questions, the methodology we use to solve them, and the key takeaway we get. So to begin, the first thing is I want to get a fine-grained understanding of server-side blocking of Tor users. To do this, we build an interactive Selenium-based crawler which can interact with these websites in the sense that it loads the front page, it tries to exercise search functionality, it tries to exercise login functionality of these websites. And then we have an automated detection of, is this user being differentiated against? And how we do this is we have a notion of what a control server sees from this website at roughly the same time. And we have a notion of what this benign Tor user sees. And we compare these to find if any form of discrimination is visible. And this discrimination could be CAPTCHAs, this could be an outright access denied page. So we start with Alexa top 500 websites. We find that 20% of these have some form of discrimination against our Tor user when they access just the front page. This is sort of where previous work was. Previous work saw front page discrimination. But we wanted to do this more fine-grained, and we also exercised the login functionality of the remaining websites and found that an additional 7.5% of these discriminate against Tor users. Now, on top of this, if a Tor user tries to access the search functionality of these websites, roughly 4% of the remaining websites also discriminate against the user. This sort of shows that the discrimination against Tor users is worse than what we understood before. The next step is I want to launch exit relays of my own and figure out how are they treated by threat intel over time and what kind of abuse traffic do they see. And additionally, I want to understand what impact does the policy of these exit relays have on either of these things. For this purpose, we launched 10 exit relays of our own. We varied two characteristics for these exit relays, the bandwidth of them and their exit policy. So our relays have three kinds of bandwidths. It's either a small, medium, or large, depending on the bandwidth of the uplink. And the exit policy could be either default, which is a more open exit policy in terms of the ports it allows traffic to go to, and reduced exit policy, which is a more conservative exit policy. It allows traffic to go through only to a small set of ports. An interesting point I want to note here is the reason we wanted to test this with reduced is because we found that there is this notion that reduced exit policy is conservative enough to prevent the blacklisting of Tor exits, and we wanted to sort of evaluate that as part of our study. I'm going to let this be at the back of your mind and move on, and I'm going to present the results from these relays in the next few slides. So the third step is I get access to abuse complaints from 25 different exit relays. These are 10 of our own and 15 exit relays that have been in the Tor network for however many years. So we get these 3 million emails from 25 exit relays. The complaints range from June 2010 to April 2016, and we want to categorize what kind of abuse has been coming from Tor over time. And the reason this is an interesting solution to the problem is, again, I don't have to log anything at the exit. I can just use these email complaints as a proxy for understanding attacks that have been launched with Tor. And yeah. So we do automatic categorization of the complaints. We do k-means clustering on the email text, and then we've got handcrafted regular expressions to get a fine-grained analysis. The approach the tools that we make for this process are about 98% accurate. And we find that a large majority of complaints that we had were about digital copyright infringement. So these were basically people trying to use Tor to do BitTorrent traffic. Since we know that these complaints are not in general that high fidelity, they are automated in general, they are sent to a whole bunch of people, we discard them from further analysis and we look only at non-DMCA complaints. Of these, we find 38% of all the non-DMCA complaints are about botnets and compromised machines. These attacks in general generate high traffic volume, which suggests that if we wanted to mitigate these attacks within the Tor network, we wouldn't need to violate the user's privacy, anonymity in any way. The other important takeaway from this was we did not find any correlation between exit policies and abuse complaints. So that thing that we were trying to test for is basically it doesn't really matter how conservative the exit policy of the Tor node is. And finally, I want to look at threat intel information and figure out how do my own relays, the relays we've launched, and those that have been in the Tor network for a while, how do they gather a bad reputation? How soon does it happen? And things like that. For this purpose, we were given access to a large data set of threat intelligence information from Facebook. We analyzed over 400 commercial IP blacklists, and we were looking for the rate at which Tor IPs get blacklisted. When I say rate, it means I have a notion of when a Tor IP first becomes an exit relay. I look at my threat intel information and figure out when was it blacklisted by a bunch of different feeds, and I see how quickly does that happen. And we find that there's an interesting phenomenon, which you can see in this graph, and I'm going to take a second to explain this. On the x-axis, I've got time until an exit relay gets enlisted on on a particular feed here. It's an example, one particular feed. And I'm showing the distribution of this over all relays. And we see that a majority of exit relays get blacklisted on this feed as soon as they are seen on the consensus. And we call this proactive blacklisting. When I say proactive, this is basically done as a matter of policy and not necessarily in response to abuse. The second phenomenon is reactive blacklisting, which is what you would expect. It's in response to some abuse that the threat intel has seen from this IP address. And that's the second plot over here, where, again, it's time until enlistment of the Tor IP address on the x-axis, and I'm showing the distribution over all exit relays. And it sort of grows slowly, showing that some bad stuff happens, and probably that's why they get enlisted on the feeds. We find that 7% of these commercial blacklists block Tor proactively, which does not bode well. Now, you remember that we had these 10 exit relays that we launched ourselves. So I'm going to try and see, I know this graph is not particularly clear, but each color on the, each colored line shows an event in the life of this relay. And I'm basically trying to see that once this relay comes up online, which is that brown line at the bottom, how quickly does it get blacklisted by different feeds? And as you can see, there are some feeds that simply seem to be crawling the consensus and putting these IPs on, and they don't take them off. So that sort of shows there's bulk long-term blacklisting by some feeds. So that's sort of the first thing I want to highlight. Then we turn our relays off for a while. And that's the second point. These feeds take a few days to realize that the relays have off, and then eventually they purge the IP address off. Once we turn our relay back on, the feeds again catch up really quickly. So the IP address gets re-enlisted very fast. But The encouraging thing is that we do find evidence of reactive blacklisting for these relays where there's short-term bans on the IP address, probably in response to abusive traffic. Okay, if my slides would. We do this analysis for all the relays we launched of different capacities and different exit policy. And we find that there was no correlation between the exit policy and the duration that an exit IP spent on any of these feeds. So I want to conclude here, and I want to talk about the key things that we learned by analyzing the dynamics of differential treatment that Tor users receive. The first thing is that undesired traffic from Tor is often high volume. And this is a line of work that I know some of my collaborators are pursuing, where there's a possibility of mitigation techniques without affecting the user's anonymity. The second thing is that blacklisting as a matter of policy seems to be fairly common. 7% of these commercial blacklists were doing this. The third thing is that we found evidence of bulk long-term blacklisting of Tor IP addresses. And also, previous work has sort of tried to figure out what is the extent of differential treatment. We go a step beyond and find that search and login functionalities are also when they are exercised, Tor users again face discrimination. And across all the experiments we did, we find that conservative exit policies are not a solution to differential treatment of Tor users. That's all.
Hi, thanks for your talk. If you just flip back to 15, there were a couple things I didn't get. So I'll go forward to show both graphs. Right. So it looks to me like, let's look at the reactive blacklisting. It looks like there are two lines which are basically right on top of each other, labeled exit IPs and non-exit IPs. If something is being blacklisted reactively, that only when something bad happens, why would a non-exit IP ever show up there? Because non-exit IPs will never appear as the source of the bad traffic.
That's true. So it doesn't make sense why any of these feeds would enlist, say, entry relay or middle relay IP addresses. But the distribution does look similar roughly, and we don't exactly know why that is the case. So we have theories. I mean, it could be that those IP addresses are also used by other services, but we don't really know.
So, but it's like, how do you know this is reactive? Is that your guess?
So we did this across 100 blacklists, and we found that some of them are very reactive, some of them are very proactive. And when we plotted this distribution of what fraction of Tor exits does a particular blacklist enlist within the first 24 hours of this relay coming online, we see that there were different percentages, and there was a clear demarcation at 30%. So that's how we made this heuristic that if a feed is enlisting more than 30% of Tor IP addresses within the first 24 hours of them taking birth on the consensus, we call it reactive.
Okay.
We call it proactive.
Proactive,
sorry. Yes,
right.
Sorry.
Okay, so they're probably not actually listing them in response to bad traffic. They're just listing them in response to some slower information update, right? Because non-exit IPs will never produce bad traffic. Yeah. Okay, so the other question I had was about DMCA complaints and how you said that the amount of complaints you get doesn't depend on your exit policy. So, right? So I've run an exit relay for years, and I'm running the reduced exit policy, which is between the default and the reduced. So I'm running the reduced exit policy. Mm-hmm. I have received 0 DMCA complaints ever. Now, it could be that I'm in Canada and the people are smart enough not to send DMCA complaints to a country that doesn't have the DMCA. I really doubt that is what's going on. I think the reduced exit policy blocking most file sharing is really what's going on. So I don't see how even the reduced exit policy, why they would be getting as many DMCA complaints as the default policy.
Right, so we did this analysis with different exit relays. For our own exit relays, we didn't really get any DMCA complaints, regardless of their policy. But we had abuse complaints from other relays that had been running for about 5 years. And we did this, we checked for correlation between their exit policy in terms of the ports they had open and the number of DMCA complaints they received over a period of time, and there was actually no correlation. So again, it's a phenomenon that for our own relays, we didn't get any abuse complaints, and then for the other exit relays, there were DMCA complaints that eventually stopped. So yeah, we thought about this, but we really did not find any correlation.
Okay, that's.
It's strange, but yeah.
We need to see that data because.
Sure, yeah.
Weird.
It sounds like an interesting discussion to continue offline. I'm going to open it up to our next questioner.
Hi, Rachee. Nice talk. So can you go back to, I think it was slide 8 or 9, where you talked about what kind of activity, can you go back one more? You know the one, yeah, this one.
Mm-hmm.
So one more, yeah. So you're saying that we knew that front page blocking was like 20%, and then if you try to log in, suddenly you are getting blocked more.
So it's the remaining websites. So there are 20% that do front page login. Now I discount those. Yeah.
And then so of the remaining, 7.48%, like normalized to the total, right?
Right.
When you try to log in, it doesn't let you log in because
right.
you're coming from Tor.
Yes.
I see. And then search just means there's a search bar and
you try to search.
And it doesn't let you.
It doesn't let. Yeah.
I see. So just curious, like, so websites like Wikipedia who let you come to the site, but won't let you edit it unless you log in.
Mm-hmm.
Then they know you're a legit person, and that should be more okay. I'm just curious, why would logging in make you disallow you? Like, why is it worse for you to try to identify yourself and say I'm authentic, be a bad thing for a website, or this maybe perhaps poor policy?
It seems like, I mean, it's a good question, but it seems like it's more a matter of policy than why it would make sense. I mean, yes, if the user is identifying themselves, then it should be easier for them to interact with the website, regardless of where they're coming from. But
so do you also have a sense of what kinds of websites these are in the red, blue, and yellow regions?
The category of these, I think there is information. There is information in the paper, but these are just Alexa top 500 websites, and it's a mixed bag of things. So you could look at the paper, and there's more information about how, say, news, shopping, social media websites are treated in specific blocking scenarios.
Cool, thank you.
Hi.
Hi.
So you mentioned 7% of IP blacklist blocking access by policy. Can you elaborate a little bit with respect to their relative popularity? So is this 7% of the N IP block list, or did you normalize for any popularity metric? I'm interested to understand what the number means.
So all of these feeds, yeah, so popularity as to who and how many people are using each of these feeds is not the information that was available to us. But yeah, that's all I have in terms of what did we know about these feeds. We just knew that they were from a part of a commercial threat exchange platform, but we don't really know who. We actually went down this path trying to identify who has this deployed, but it was very hard to see that correlation just by interacting with the website.
Yeah.
So, yeah.
And I would imagine that there are lots of organizations using multiples, so then you can overlap. Is that also your?
Yes, that is the case. We also see, so if you look at so there are those two blacklists that seem to be very much synchronous. So it seems like they are kind of related to each other in some way. So that is the case, that they have some, there's a significant intersection between different blacklists.
Yeah. Thanks.
We have time for one more question if you want to go ahead, and I know there are other questions certainly for offline, so please do find the speaker afterwards. Go ahead.
Hi, nice talk. I'm Susan from Carnegie Mellon. So I was wondering whether you have considered rate limiting. For instance, as a Tor user, I can totally imagine somebody wanting to slow you down to demotivate you from using Tor. So maybe I was wondering if you consider that sort of a differential treatment rather than just blacklisting.
No, in this study we were basically looking, that's a great question, but we were looking at differential treatment in terms of if I access this from a control server versus I access this as a Tor user, do I see any difference?
Right, because I imagine for rate limiting, it might be harder for you to give a hard, it's not really a binary yes or no, right? So it can be some differential, like network link speed and so on. So it might be interesting future. Maybe we can talk offline about that too.
Right, because I know there are state level sensors that sort of do that. So yeah. That's a good idea. Thank you.
All right, let's thank our speaker one more time, please.